You pick up a tiny grain of sand, hold it out in front of your eyes, and look up at the sky. The patch of darkness that grain of sand blocks right now is hiding 800,000 galaxies. 800,000. Each one contains billions, even trillions of stars. This is not imagination. This is not science fiction. This is real data, captured by the James Webb Space Telescope. For decades, we believed the universe was about 14 billion light-years across. That is what textbooks said. That is what scientists taught. But now we know the true number is 93 billion light-years. The universe is far larger than we ever thought. And the most unsettling part? James Webb is seeing things that should not exist at that moment in cosmic history. Galaxies that are too massive, too bright, appearing far too early. Supermassive black holes growing faster than the laws of physics should allow. Stars forming at a completely insane pace within the first few 100 million years. Everything we thought we knew about how the universe formed, how galaxies grew, how stars were born, is starting to fall apart. The scientific models astronomers spent decades building no longer match reality. The universe was not slow or patient like we imagined. From the very beginning, it was explosive, chaotic, and violent. Do you want to know the truth hidden out there? Do you want to see what James Webb is discovering every single day? Hit the like button and subscribe to the channel right now, because this journey will change the way you see the universe forever. To understand what James Webb is revealing to us, we first need to understand how this incredible machine actually works. Think about looking at a star tonight. The light you see didn't just leave that star moments ago. The nearest star beyond our own sun is over 4 light-years away. This means the light hitting your eyes right now left that star 4 years in the past. You're literally looking backward in time every time you look up at the night sky. James Webb takes this concept to an extreme that's hard to wrap your mind around. This telescope doesn't look at stars from 4 years ago. It stares at objects so impossibly distant that their light has been traveling through space for over 13 billion years. 13 billion. The telescope is essentially a time machine, showing us snapshots of the universe when it was just a baby, when the first stars were being born, when everything was still forming. The genius of James Webb lies in how it sees. Your eyes detect visible light, the colors of the rainbow you can see with your own vision. The Hubble Space Telescope, which came before Webb, also mostly saw invisible light. But James Webb is completely different. It doesn't see like you see. Instead, it captures something called infrared radiation, which is completely invisible to human eyes. Why does this matter so much? The answer lies in one of the most important discoveries in all of astronomy: the universe is expanding. Space itself is growing larger every single second. As it grows, it stretches everything inside it, including light waves traveling through the void. Light that started its journey as ultraviolet or visible radiation gets pulled, stretched, lengthened as it crosses billions of light-years of expanding space. By the time this ancient light reaches us, it has shifted completely into infrared wavelengths. This stretching effect is called redshift, because the light shifts toward the red end of the spectrum, then beyond into infrared. The farther away something is, the more its light gets stretched during its journey to us. This creates a problem for telescopes that only see visible light. Objects from the early universe become completely invisible to them because their light has been redshifted right out of the visible spectrum. Hubble couldn't find galaxies like the ones James Webb is discovering because their light had shifted beyond what Hubble's instruments could detect. They were hiding in plain sight, waiting for a telescope that could see in infrared. James Webb sits at a very special location in space called Lagrange Point 2, positioned about 930,000 miles from Earth. This might seem like a random spot, but it's actually perfect for what the telescope needs to do. At this location, Webb stays in permanent shadow from both Earth and the Sun. It never gets hit by direct sunlight. This positioning is absolutely critical for one simple reason: heat. Infrared sensors must be kept incredibly, almost impossibly cold to work properly. When they heat up, they start producing their own infrared glow, which drowns out the faint signals coming from distant galaxies. It would be like trying to see stars at night while someone shines a flashlight directly in your eyes. To avoid this, Webb's instruments operate at around -370 degrees Fahrenheit. That's colder than the surface of Pluto. That's colder than most places in our solar system. The telescope sits out there in the freezing darkness of space, quietly gathering ancient photons. The telescope's primary mirror is a work of engineering art. It spans 21 feet across, made up of 18 separate hexagonal segments that fit together like a golden honeycomb. Each segment is coated with an ultra-thin layer of gold because gold reflects infrared light better than any other material we can use. The segments aren't just sitting there in a fixed position either. Each one can be adjusted individually by tiny motors, allowing the entire mirror to focus perfectly on whatever distant object astronomers want to study. This precision engineering means Webb can collect light from objects 100 times fainter than what Hubble could see. Imagine trying to spot a firefly on the moon from Earth. That's the level of sensitivity we're talking about. The telescope can detect the faintest whispers of light that have been traveling through space since the dawn of time. Here's how it actually finds these ancient galaxies. Astronomers program Webb to observe specific patches of sky for hours, sometimes even days at a time. The telescope just sits there, staring at one spot, not moving. The longer it stares, the more faint light it gathers. Photons that left distant galaxies billions of years ago trickle in one by one, like raindrops filling a bucket. Webb's detectors count them, accumulating them over time. Slowly, gradually, an image builds up. Galaxies that would be completely invisible with a shorter observation period become visible through sheer patience. Once the image is captured, the real detective work begins. Webb has special instruments called spectrographs that analyze the light in incredible detail. These devices split the incoming light into individual wavelengths, creating what scientists call a spectrum. Think of it like using a prism to split white light into a rainbow, except far more precise. Every element in the universe emits light at specific wavelengths, creating a unique fingerprint that nothing else can replicate. Hydrogen looks different from helium when you examine their light closely enough. Oxygen looks different from carbon. By reading these fingerprints embedded in the light from distant galaxies, Webb can determine exactly what those galaxies are made of, how fast they're moving through space, what kinds of stars they contain. Most importantly, the spectrum reveals how far away the galaxy is. This is where redshift measurements come into play. By examining how much the light has been stretched during its journey, astronomers can calculate the precise distance to the object. The more stretched the light, the farther away it is, the longer the light has been traveling, the further back in time we're looking. What makes this process both beautiful and terrifying is the scale of what we're seeing. Every deep field image Webb captures reveals thousands upon thousands of galaxies. Each one is an entire world we will never visit, a collection of billions or trillions of stars located so far away that we're seeing them as they existed when the universe was young. Some of these galaxies don't even exist anymore in their current form. They've merged with other galaxies, been torn apart by collisions, evolved into something completely different. We're seeing them frozen in time, preserved in light that has been crossing the void for eons. The Hubble Space Telescope gave us our first deep looks into the universe's past, revealing galaxies billions of light-years away. But Hubble was limited by its visible light vision. It could only see so far back before galaxies faded from view, their light shifted beyond detection. James Webb smashes through that barrier. It pushes deeper into cosmic history than any telescope before it. Every observation extends our view further into the past, closer to the Big Bang itself, revealing epochs of time that were previously hidden from us. When James Webb began looking, it discovered something nobody expected. Imagine looking at the universe when it was only 2% of its current age. Close your eyes for a moment. Picture absolute darkness. Not the darkness of night where stars shine overhead, but true, complete darkness stretching in every direction. No light anywhere. Just hydrogen and helium gas floating in the void, cold and silent. This was the universe for its first few 100 million years. Astronomers call this period the Cosmic Dark Ages, a name that perfectly captures what it must have been like. During this time, no stars existed yet. No galaxies lit up the darkness. The Big Bang had happened, space was expanding, matter was spreading out, but nothing was shining. Just endless night filled with invisible gas clouds drifting through the emptiness. The Dark Ages lasted much longer than most people would expect, stretching across hundreds of millions of years of cosmic history. Then something changed. Gravity, that invisible force pulling everything together, finally won its long, slow battle. The gas clouds began collapsing in on themselves. As they collapsed, they grew denser. Pressure built inside them. Temperatures climbed higher. The hydrogen atoms packed closer together, compressed by the weight of the gas above them. When the temperature at the core of these collapsing clouds reached about 10 million degrees, something magical happened. Nuclear fusion ignited. Hydrogen atoms began fusing together into helium, releasing tremendous amounts of energy in the process. A star was born. Then another. Then millions more. Light flooded into the universe for the first time since the Big Bang's initial flash. This moment marked the end of the Dark Ages. This was the cosmic dawn, when the universe went from darkness to light, when the first stars began burning, when everything we can see today started taking shape. The galaxy called JWST 14 formed during this cosmic dawn. Light left this galaxy just 280 million years after the Big Bang. That might sound like a long time, but in cosmic terms, it's nothing. It's a blink. To put this in perspective, the universe today is 13.8 billion years old. JWST 14 existed when only 2% of that time had passed. Imagine if the universe's entire history was compressed into 1 year. This galaxy would have formed on January 7th. We're looking at cosmic infancy, at a time when everything was new, raw, barely formed. The discovery happened because James Webb was specifically designed to hunt for objects like this. The telescope searched through its infrared images looking for candidates, galaxies that appeared extremely red because their light had been stretched so much during its journey. When astronomers spotted the faint signal from JWST 14, they turned the telescope back toward it in April of 2025 for confirmation. They needed to be absolutely certain this wasn't a mistake, not a closer object masquerading as something distant. The spectroscopy came back crystal clear. The measurements were confirmed. This was not a theory, not speculation based on blurry images. This was real data proving this galaxy existed at the edge of what we can observe, nearly as far back as any telescope has ever seen. The galaxy has a redshift value of 14.44. That number represents extreme distance, extreme age. It beat the previous record holder by just 10 million years, which sounds small until you realize that in the early universe, 10 million years represented massive changes. Everything was evolving incredibly fast back then. What shocks scientists about JWST 14 is that it's not some tiny speck barely visible in Webb's images. The galaxy is bright. It's actively forming stars during what appears to be a burst of rapid creation. When astronomers analyzed its spectrum, they found nitrogen inside it. Nitrogen. This discovery is absolutely critical because nitrogen doesn't exist naturally in the universe. It has to be created inside stars through nuclear fusion, then scattered into space when those stars explode. The presence of nitrogen means at least one generation of stars, possibly two, had already lived their entire lives inside this galaxy by the time we're seeing it. These stars formed, burned through their fuel over millions of years, exploded as supernovas, scattered their enriched material into the surrounding gas clouds. Then new stars formed from that enriched gas, incorporating the nitrogen and other heavy elements created by their stellar ancestors. This sequence of events takes time. Each step requires millions of years minimum. Stars don't form instantly. They need time to condense from gas clouds. They need time to burn their fuel. The biggest stars, the ones that create elements like nitrogen, live fast but still require millions of years before they explode. Then you need time for the next generation of stars to form from the debris. JWST completed all of this, multiple stellar generations, in less than 300 million years. The timeline is compressed almost impossibly tight. According to older models, galaxies were supposed to grow slowly, carefully, over hundreds of millions or even billions of years. Small clumps of stars would form first, then gradually merge together into larger structures. The process was thought to be gradual, methodical, taking its time. JWST proves those models wrong. The galaxy didn't grow slowly. It exploded into existence, forming stars rapidly, cycling through stellar generations at breakneck speed. Everything happened fast, much faster than our theories predicted was possible. Compare this to our own Milky Way galaxy. The Milky Way has existed for over 13 billion years. It has had enormous amounts of time to go through countless cycles of star birth and death. It has had time to build up a rich inventory of heavy elements like carbon, oxygen, nitrogen, iron. Earth itself contains iron in its core, silicon in its rocks, gold and uranium scattered through its crust. Every single one of those elements heavier than hydrogen and helium came from ancient supernovas that exploded billions of years ago, enriching the gas clouds that eventually formed our solar system. JWST started that same process of stellar enrichment in a tiny fraction of the time the Milky Way had available. The galaxy was already producing nitrogen-rich stars when the universe was barely out of its infancy. This speaks to processes we don't fully understand, to mechanisms that made early galaxy formation more efficient than modern galaxy formation. JWST is not alone either. James Webb has found over 100 galaxies from this same early period of cosmic history. Each one is bright, each one is actively forming stars, each one is challenging the models that predicted slow, gradual galaxy formation. The cosmic dawn was not a gradual brightening like sunrise on Earth. It was an explosion of activity, a burst of galaxy formation that lit up the universe in a relatively short time. Galaxies appeared fast during this period, shining intensely, transforming the universe from darkness into light within just a few 100 million years. We're only now seeing the evidence because light takes that long to reach us. The photons that left JWST have been traveling through expanding space for over 13 billion years, crossing unimaginable distances to finally arrive at James Webb's golden mirrors. What this discovery tells us is profoundly unsettling for cosmologists who spent decades building models of the early universe. The universe does not follow the slow, careful progression we expected. It moves fast when conditions are right. The forces driving galaxy formation in the early universe were stronger, more efficient than anything we observe in the modern cosmos. Gas collapsed faster. Stars formed more readily. Feedback mechanisms that slow down star formation in today's galaxies were weaker or completely absent back then. The early universe was a more productive, more violent, more chaotic environment for building galaxies than we ever imagined. Every discovery like JWST forces astronomers to go back to their computer simulations, adjust their parameters, revise their timelines. The picture of cosmic history is being rewritten in real time as James Webb continues its observations. But this is just the beginning. James Webb found something far more terrifying lurking in the early universe. Something is feeding out there. Feeding faster than every law of physics should allow. Deep in the darkness of the early universe, barely 500 million years after the Big Bang, sits a galaxy with the designation Canucks LRD Z86. At first glance, it might seem like just another distant galaxy among thousands. But when astronomers pointed James Webb's instruments at this object, when the spectrum came back, when they analyzed what they were seeing, they realized something impossible was happening inside this galaxy. There's a black hole at its center. Not just any black hole, but a supermassive monster weighing millions of times more than our Sun. It's sitting there, spinning in the darkness, pulling in matter from its surroundings. Gas spirals around it in a glowing disk, heating to millions of degrees as it falls toward the event horizon. The black hole is feeding, consuming everything that gets too close, growing larger with every passing moment. Here's the problem that keeps scientists awake at night: this black hole should not exist. Not at this time in cosmic history. Not at this size. There simply hasn't been enough time for it to grow this massive. Black holes form when massive stars collapse. Picture a star 20 times heavier than our Sun burning through its nuclear fuel. When it runs out of energy to hold itself up against gravity's crushing force, the core implodes in a fraction of a second. The collapse is so violent, so complete, that it creates a black hole. But these stellar mass black holes are relatively small in cosmic terms. They might weigh 50 times what our Sun weighs, maybe 100 times at most. Supermassive black holes are completely different beasts. They weigh millions or even billions of times more than our Sun. The black hole at the center of our Milky Way weighs about 4 million times what the Sun weighs. Some supermassive black holes tip the scales at billions of solar masses. They're so massive that their gravity dominates entire galaxies, holding billions of stars in orbit around them. The question that haunts astronomers is simple: how do you get from 50 solar masses to millions? The answer, according to standard theories, is time. Lots of time. The black hole has to eat. It has to consume gas and dust floating through space. It has to swallow stars that wander too close. Each meal adds a little more mass. Slowly, gradually, over hundreds of millions or billions of years, the black hole grows from stellar mass to supermassive. Canucks LRD Z86 didn't have that kind of time. The universe was barely 570 million years old when this galaxy existed as we're seeing it. That's nowhere near enough time for a black hole to grow through normal feeding from stellar mass to supermassive. The math simply doesn't work. The black hole would have needed to consume matter constantly, without pause, at maximum efficiency for the entire history of the universe up to that point. Even then, it probably couldn't have grown this large this fast. Yet there it sits, confirmed by spectroscopy from James Webb. Not a theory, not a guess based on fuzzy images. Real data showing real light coming from gas falling into a real supermassive black hole that, according to our understanding of physics and time, should not be there yet. This galaxy belongs to a class of objects astronomers are calling little red dots. The name sounds almost cute until you understand what these things actually are. They appear as small, faint, extremely red smudges in James Webb's images because their light has been stretched by billions of years of cosmic expansion. Webb has discovered dozens of these objects since it began operations. Most of them confuse and disturb astronomers because they break fundamental rules about how galaxies and black holes should work. Canucks LRD Z86 falls into the most troubling category. The black hole at its center outweighs the galaxy's stars by a significant margin. In normal galaxies, the central black hole weighs maybe 0.1% of the total stellar mass. The black hole is there, it's important, but it's a tiny fraction of the galaxy's total weight. In Canucks LRD Z86, that ratio is completely inverted. The black hole weighs as much as or more than all the stars combined. The tail is wagging the dog. The relationship between galaxy and black hole is backwards. So how did this monster form so quickly? Astronomers have developed two main theories, though both have serious problems. The first theory involves direct collapse. Normally, gas clouds collapse to form stars first, then those stars collapse to form black holes. But under very specific conditions, a massive gas cloud might skip the star formation step entirely. It could collapse directly into a black hole, creating what scientists call a heavy seed. This heavy seed might weigh thousands of times more than the Sun right from birth, giving the black hole a massive head start on its growth. Instead of starting at 50 solar masses, it starts at 10,000 or more. The problem with this theory is that direct collapse requires an incredibly specific set of conditions. The gas needs to be pristine, unpolluted by heavy elements. It needs to be hot enough to prevent normal star formation but dense enough to collapse under its own gravity. The region needs to be bathed in intense ultraviolet radiation from nearby sources to keep the gas from cooling and fragmenting. All of these conditions happening in the same place at the same time seems unlikely, yet if direct collapse wasn't occurring, where did these early supermassive black holes come from? The second theory involves supermassive stars. These hypothetical objects would be hundreds or even thousands of times heavier than normal stars. They would burn incredibly hot and bright, living fast and dying young. When they collapsed, they would leave behind black holes that were already heavy, potentially tens of thousands of solar masses. These heavy remnants could then grow to supermassive size much more quickly than black holes that started from normal stellar collapse. The problem here is that supermassive stars are purely theoretical. We've never observed one. We don't know for certain they can form, how common they might be, or what conditions would create them. They exist in computer simulations but not in our observational data. Yet something must have created these early supermassive black holes because we can see them now, sitting in galaxies from the cosmic dawn. What makes Canucks LRD Z86 even more disturbing is how fast it's feeding. James Webb detected gas swirling around the black hole at incredible speeds. The spectrum shows the gas is highly ionized, meaning radiation from the black hole has stripped electrons from atoms, leaving them electrically charged. This is a signature of rapid accretion, of matter falling into the black hole at tremendous rates. When astronomers calculated the feeding rate, they found something that shouldn't be possible. The black hole is consuming matter more than 40 times faster than the theoretical Eddington limit. This limit represents the maximum rate at which a black hole should be able to feed before its own radiation pushes away incoming matter. Here's how the limit works. When matter falls toward a black hole, it doesn't just drop straight in. It forms a swirling disk around the event horizon called an accretion disk. Friction within this disk heats the matter to millions of degrees. Hot matter emits radiation, particularly intense X-rays. This radiation pushes outward in all directions. The faster matter falls in, the more radiation gets produced, the stronger the outward pressure becomes. Eventually, you reach a point where the radiation pressure becomes strong enough to blow away the incoming material. The black hole essentially chokes itself. Matter can't fall in any faster because the radiation pressure equals the gravitational pull. This creates a natural speed limit on black hole feeding. It's called the Eddington limit after the astronomer who first calculated it. Canucks LRD Z86 black hole is exceeding that limit by a factor of 40. 40 times. Not 10% faster. Not twice as fast. 40 times faster than physics says should be possible. It's like discovering a car with a top speed of 100 miles per hour somehow traveling at 4,000 miles per hour. The numbers don't make sense according to what we know about how black holes work. One possibility is something called super-Eddington accretion. This can happen when matter falls in from all directions simultaneously, overwhelming the radiation pressure through sheer volume. Imagine trying to stop a tidal wave with a fan. The wave wins because there's simply too much water coming from too many directions. The fan's air resistance can't push it all back. Something similar might be happening with this black hole. If enough gas collapses onto it at once from multiple directions, the radiation might not be able to push it all away fast enough. The black hole gorges itself in a short, intense burst of feeding. These episodes are likely rare and short-lived. A black hole can't sustain super-Eddington accretion for millions of years because the surrounding gas supply would run out. What makes this observation so important is that astronomers caught the black hole during this brief phase. It's a snapshot of rapid growth captured in the act. If these feeding frenzies happened regularly in the early universe, if many young black holes went through periods of super-Eddington accretion, it could explain how they grew so massive so quickly. Each burst would add significant mass in a relatively short time. Over multiple episodes, a black hole could grow from stellar mass to supermassive in far less time than normal steady accretion would require. The black hole's current mass is relatively small for a supermassive black hole, only a few million times heavier than our Sun. That makes sense given how young the universe was when this galaxy existed. What doesn't make sense is how bright it is. The energy pouring out of the accretion disk is enormous. X-rays scream into space. The surrounding gas glows with intense heat. The luminosity suggests this black hole is feeding at an absolutely ferocious rate. If this feeding rate continued for just a few million years, the black hole would double in size. Do that 10 times over 100 million years, doubling 10 times through repeated Super Eddington episodes, you could grow from thousands of solar masses to millions. The timeline starts to work, barely, if these feeding frenzies were common in the early universe. Scientists think events like this might have been standard during the cosmic dawn. Gas was denser back then because the universe was smaller, everything was packed closer together. Galaxies were still forming, their structure chaotic and unstable. Massive gas clouds could collapse directly onto young black holes, triggering these intense feeding episodes. Each burst would add mass quickly. Over time, through multiple episodes interspersed with periods of slower growth, a black hole could reach supermassive size far faster than steady feeding would allow. James Webb's discovery of Canucks LRD Z86 and its violently feeding black hole provides critical evidence for this theory. Before Webb, Super Eddington accretion was hypothetical, something that happened in computer simulations but had never been directly observed in the early universe. Now we have proof. We have measurements. We know it happens. The question shifts from whether it's possible to how often it occurred, how many black holes grew this way, how important these feeding frenzies were to building the supermassive black holes we see in galaxies today. These black holes aren't alone. They're everywhere, hiding inside the strangest objects ever discovered. Tiny red smudges appearing everywhere. They're breaking every rule we thought we knew. James Webb started finding them almost immediately after it began observations. Tiny red smudges scattered across its deep field images like droplets of blood on black velvet. At first, astronomers thought they were looking at just another batch of distant normal galaxies. Ancient objects, yes, far away certainly, but nothing particularly unusual. Then the spectroscopy results started coming back. These objects are not normal. Not even remotely close to normal. They're compact, extremely luminous for their size, their properties make absolutely no sense according to our models of galaxy formation. Scientists started calling them little red dots because that's exactly what they look like in the images. Small points of red light, faint but definitely there, scattered throughout the early universe. Over 100 of these objects have been identified so far, probably many more waiting to be confirmed. They all share certain traits that make them stand out from regular galaxies. First, they're incredibly small, much smaller than typical galaxies from the same time period. Where you might expect a galaxy to span tens of thousands of light-years across, these little red dots are compressed into regions just a few thousand light-years wide. They're dense, packed tight, concentrated in a way that normal galaxies aren't. Second, they're red because their light has been stretched by cosmic expansion. This isn't unusual by itself. Distant objects appear red due to redshift. But little red dots are redder than they should be based on their distance alone. Something about their internal properties makes them emit light that's already shifted toward the red end of the spectrum before cosmic expansion even touches it. Third, they're bright. Way too bright for their size. When you calculate how much light they're producing, the numbers don't match what you'd expect from a galaxy of that size and mass. It's like looking at a flashlight that's somehow producing as much light as a searchlight. The energy output doesn't make sense. Fourth, they contain either extremely dense clusters of stars or massive black holes that shouldn't fit inside them. Both options break our understanding of how galaxies work. Let's explore the first possibility. Suppose the brightness comes from stars packed incredibly tightly together. You can calculate how many stars you'd need to produce that much light. When astronomers did the math for little red dots, they got numbers that are physically impossible. The stars would be packed so tightly that they'd be constantly colliding with each other. They'd merge, coalesce, create chaos. This level of stellar density doesn't exist in any galaxy we observe in the modern universe. Stars need space. Even in the densest star clusters we know about, stars maintain some distance from each other. They orbit the cluster's center of gravity without constantly running into their neighbors. The collision rate is low. In little red dots, if stars were producing all that light, they'd be so close together that collisions would be happening constantly. Stars would be merging all the time, creating bigger stars that would burn out quickly. The whole system would be unstable, rapidly consuming itself. The alternative explanation is even more troubling. Maybe the light isn't coming from stars at all. Maybe it's coming from a supermassive black hole at the center, with matter falling into it producing the intense radiation. This would explain the brightness because black holes feeding on matter can produce enormous amounts of energy from a very small region. But this creates a different problem. In modern galaxies, there's a well-established relationship between the black hole at the center and the galaxy surrounding it. The black hole typically weighs about 0.1% of the galaxy's total stellar mass. Maybe slightly more, maybe slightly less, but always in that general range. The galaxy and its black hole grow together, maintaining a balanced ratio over time. In little red dots, this relationship is completely inverted. The black hole can weigh as much as the entire galaxy's stars combined. Sometimes it weighs even more. The ratio is backwards, upside down, wrong. It's like finding a dog with a tail that weighs more than the dog itself. The proportions make no sense. This suggests the black hole formed first, growing to enormous size before the galaxy had time to build up a comparable stellar population. But how? Black holes need galaxies to feed them. They consume gas from their surroundings. Without a galaxy to provide material, what did these black holes eat to grow so large? Where did the mass come from? Astronomers thought they understood how galaxies and their central black holes evolved together. The galaxy forms first, building up stars over millions of years. As it grows, gas slowly filters toward the center, feeding a small black hole that gradually increases in mass. The two components grow in tandem, keeping pace with each other, maintaining their mass ratio. Eventually they reach equilibrium, settling into the relationship we observe in modern galaxies. Little red dots show this entire narrative is wrong, at least for the early universe. The black hole got huge first, somehow acquiring millions of solar masses while the surrounding galaxy was still tiny. The black hole overpowered the galaxy around it, dominating the system's total mass. This is backwards from everything our models predicted. Another deeply disturbing aspect of little red dots is their abundance. Before James Webb, astronomers expected to find maybe a handful of unusual galaxies in the early universe. Outliers, rare exceptions to the general rules of galaxy formation. Instead, Webb found hundreds. They're not rare oddities at all. They're common, appearing at multiple distances, existing throughout the first billion years of cosmic history. This means whatever process created little red dots wasn't a fluke or an accident. It was a standard part of how the early universe worked. Some significant fraction of early galaxies went through this phase where their central black hole dominated their mass budget. This was normal back then, even though it never happens in the modern universe. Some scientists think little red dots might be transition objects, snapshots of galaxies caught in the middle of a growth spurt. Perhaps the central black hole feeds rapidly during an early phase, growing to enormous size quickly. Meanwhile, the surrounding galaxy is still assembling, still building up its stellar population. We're catching these systems during the brief period when the black hole is temporarily larger than the galaxy. Over time, according to this interpretation, the galaxy would catch up. It would keep forming stars, keep growing, eventually building up enough stellar mass to restore the normal ratio. The little red dot would mature into a normal quasar, those bright objects powered by supermassive black holes that we see scattered throughout the universe. Little red dots would be baby quasars, glimpses of these objects during their youth before they fully developed. Other scientists think little red dots might represent a completely different formation pathway that doesn't exist anymore. Maybe in the early universe, conditions allowed black holes to form first, growing massive before their host galaxies assembled around them. Maybe dark matter played a bigger role than we realized, creating gravitational wells that trapped gas and allowed black hole formation before significant star formation occurred. Maybe the early universe had different rules, different physics at work. Gas was denser, temperatures were higher, radiation fields were more intense. These conditions might have enabled formation processes that simply can't happen in the modern, cooler, more diffuse universe. Little red dots could be relics of that different epoch, showing us what galaxy formation looked like when the cosmos was young and wild. One thing is absolutely certain, little red dots are not going away. Every new observation James Webb makes finds more of them. They appear at multiple redshifts, meaning they existed throughout the first billion years, not just at one specific moment. They weren't limited to a particular era. They were everywhere during the cosmic dawn, scattered across space like cosmic mysteries waiting to be solved. The most profoundly unsettling part is what little red dots say about our theoretical models. Astronomers built equations describing how galaxies should form. They ran massive computer simulations testing those equations, watching virtual galaxies evolve over billions of years of simulated time. The simulations predicted slow, steady growth. They predicted galaxies forming stars gradually over billions of years. They predicted black holes staying small relative to their host galaxies, growing in lockstep with stellar populations. Little red dots break all three predictions simultaneously. They're small but bright. Their black holes are enormous relative to their stellar mass. They appeared early and remained common for hundreds of millions of years. Every single one challenges our understanding of early galaxy evolution. The universe was not patient during its youth. It didn't follow the slow, methodical processes our simulations predicted. Instead, it was chaotic, fast, intense, violent. Gas collapsed rapidly. Black holes grew at ferocious rates. Stars formed in massive bursts. Everything happened quickly, compressed into timescales that seem impossibly short based on our models. Little red dots are the proof, scattered across James Webb's images like evidence at a crime scene. They're telling us our theories are incomplete, our models are missing something fundamental. Whatever processes dominated galaxy formation in the early universe were different from what we see today, more efficient, more extreme, operating under different rules or different conditions. But these black holes don't just sit there glowing. Some are doing something even more impossible. Physics has limits. Hard rules about how fast black holes can consume matter. One black hole is ignoring those rules completely. Physics isn't just a collection of interesting facts about how the universe works. It's a set of fundamental constraints, boundaries that govern what's possible and what's not. Some things simply cannot happen because the laws of physics forbid them. You can't travel faster than light. You can't create energy from nothing. You can't cool anything below absolute zero. These aren't suggestions or guidelines. They're ironclad rules enforced by the structure of reality itself. Black holes have their own set of rules. One of the most important is called the Eddington limit, named after the British astronomer Arthur Eddington who first calculated it in the early 20th century. This limit describes the maximum rate at which a black hole can consume matter before its own radiation pushes that matter away. It's a speed limit on feeding, a natural break that prevents black holes from growing infinitely fast. A black hole named LID 568 is completely ignoring this limit. Astronomers have no idea how it's doing this. LID 568 sits at the center of a dwarf galaxy, visible as it existed 1.5 billion years after the Big Bang. Both James Webb and the Chandra X-ray Observatory observed it, combining their data to build a complete picture of what's happening. When the measurements came back, when scientists calculated the feeding rate, they found something that shouldn't be possible according to our understanding of physics. The black hole is consuming matter at over 40 times the Eddington limit. 40 times. Not 10% faster than the limit. Not twice the limit. 40 times faster than the theoretical maximum rate physics says should be possible. To understand why this is so shocking, you need to understand how the Eddington limit works. When matter falls toward a black hole, it doesn't just plunge straight into the event horizon. The matter has angular momentum, sideways motion that prevents it from falling directly inward. Instead, it spirals around the black hole, forming a flat rotating disk called an accretion disk. This disk is not a calm, peaceful place. Matter in the inner regions orbits faster than matter in the outer regions, creating tremendous friction as different parts of the disk slide past each other. This friction generates heat, enormous amounts of heat. The temperature in the accretion disk can reach millions of degrees, hot enough to strip electrons from atoms, hot enough to emit intense radiation across the electromagnetic spectrum. The hottest regions near the black hole blast out X-rays, high-energy photons that carry tremendous momentum. These X-rays don't just disappear into space. They interact with the infalling matter, pushing against it. Every photon that hits an atom of gas transfers a tiny bit of momentum, exerting pressure outward, away from the black hole. Normally, this radiation pressure is relatively weak compared to gravity's inward pull. Matter keeps falling in despite the outward pressure. But as the feeding rate increases, as more matter falls in per second, the accretion disk gets hotter and brighter. More X-rays get produced. The radiation pressure grows stronger. Eventually, you reach a critical point where the outward radiation pressure exactly balances the inward gravitational pull. Matter can't fall in any faster because the radiation is pushing it away with exactly the same force that gravity is pulling it inward. The system reaches equilibrium. This is the Eddington limit. Think of it like trying to pour water into a bucket while someone is blowing air up from the bottom. Pour slowly, the air doesn't matter. Pour faster, the air starts disrupting the water flow. Pour fast enough, the air pressure becomes strong enough to blow the water back out. You've reached the limit of how fast you can fill the bucket against the air resistance. For black holes, the Eddington limit creates a natural speed cap on growth. A black hole can't grow infinitely fast by gobbling up matter because its own radiation chokes off the supply once feeding reaches a certain rate. This is why black hole growth takes time. The limit forces them to grow slowly and steadily rather than ballooning up instantly. LID 568 is somehow feeding at 40 times this theoretical maximum. 40 times. It's like saying a car with a top speed of 100 miles per hour is somehow cruising down the highway at 4,000 miles per hour. The speedometer reading makes no sense. The physics doesn't support it. Yet the measurements are clear. This black hole is gorging itself at a rate that should be physically impossible. One possible explanation involves what astronomers call super-Eddington accretion. This happens when matter falls in from multiple directions simultaneously, overwhelming the radiation pressure through sheer volume and geometry. Imagine standing in a rainstorm trying to stay dry by holding up an umbrella. The umbrella works fine if rain is only falling from above. But if water is coming from the sides too, from below, from every angle at once, the umbrella becomes useless. You get soaked no matter how good your umbrella is. Something similar might be happening with LID 568. If massive amounts of gas are collapsing onto the black hole from all directions at once, the radiation pressure can't push it all away. The radiation primarily pushes outward along the plane of the accretion disk, creating the strongest pressure in certain preferred directions. But if gas is falling in from the poles, from above and below the disk plane, it might avoid the strongest radiation pressure zones entirely. It could pour into the black hole despite the intense radiation screaming outward. Alternatively, the infalling matter itself might be so dense, so optically thick, that radiation can't escape easily. The photons get trapped in the dense gas, scattered and absorbed before they can push the material away. The radiation pressure is still there, still being generated, but it can't efficiently transfer momentum to the infalling matter because the gas is too thick, too opaque. These super-Eddington feeding frenzies are probably short-lived events. A black hole can't sustain this kind of extreme feeding for millions of years. The surrounding gas supply would run out. Even the densest gas clouds can only provide so much material. Once the local reservoir is depleted, the feeding rate would drop back down to normal or below normal levels as the black hole waits for more gas to become available. What makes LID 568 critically important is that astronomers caught it during this brief phase. It's a snapshot of a black hole in the act of gorging itself, growing at breakneck speed during what might be a relatively rare episode. The observation proves that super-Eddington accretion actually happens. It's not just a theoretical possibility that exists in computer simulations. It's real, observable, measurable. The black hole's current mass is relatively modest for a supermassive black hole, only a few million times heavier than our Sun. That makes sense given how young the universe was at this point in cosmic history. There simply hasn't been enough time for it to grow truly gigantic yet. But what doesn't make sense is its brightness, the sheer amount of energy pouring out of its accretion disk. X-rays scream into space with intensities that require enormous amounts of matter falling inward. The energy output is staggering. If this feeding rate continued for just a few million years, the black hole would double in mass. That might not sound impressive until you realize what it means over longer timescales. Double the mass in 5 million years. Wait another 5 million, double it again. That's 4 times the original mass in 10 million years. Keep going. 8 times in 15 million years. 16 times in 20 million years. Through repeated episodes of super-Eddington feeding, each lasting just a few million years with breaks in between, a black hole could grow from thousands of solar masses to millions in far less time than steady Eddington-limited feeding would require. Scientists increasingly believe events like what we're seeing with LID 568 might have been common throughout the early universe. Gas was denser back then because everything was compressed into a smaller volume. The universe was smaller, matter was packed closer together, collisions and interactions were more frequent. Galaxies were still forming, their structures chaotic and unstable, not yet settled into the orderly spirals and ellipticals we see in the modern cosmos. In this environment, massive gas clouds could collapse directly onto young black holes without fragmenting into stars first. The collapse would trigger intense super-Eddington feeding episodes, brief but powerful bursts where the black hole consumed matter at rates far exceeding the Eddington limit. Each episode would add significant mass quickly. Over hundreds of millions of years, through multiple episodes interspersed with quieter periods of slower growth, a black hole could reach supermassive size much faster than our traditional models predicted. James Webb's discovery of LID 568 provides concrete evidence for this scenario. Before this observation, super-Eddington accretion in the early universe was purely hypothetical. Astronomers suspected it might happen based on theoretical calculations and computer simulations, but they had no proof. Now we have direct observational evidence. We've measured it. We know the feeding rate. We've confirmed it's real. The question now shifts from whether super-Eddington accretion is possible to how often it occurred. Was LID 568 an extremely rare event, a 1 in a billion occurrence we happened to catch by pure luck? Or were these feeding frenzies common, happening regularly throughout the cosmic dawn, affecting thousands or millions of black holes as they grew towards supermassive size? The answer matters enormously for our understanding of cosmic history. If super-Eddington episodes were common, they could explain how supermassive black holes reached billions of solar masses within the first billion years after the Big Bang. If they were rare, we need different explanations, other mechanisms to account for the rapid black hole growth we're observing. Every new observation from James Webb adds another piece to this puzzle. Every black hole it studies, Every feeding rate it measures, every spectrum it analyzes contributes to building a more complete picture of how these cosmic monsters grew so large so quickly when the universe was young. While individual black holes break the rules, stepping back reveals something even more staggering about the universe itself. Hold a grain of sand at arm's length. Look at the sky. You know what's hiding behind it. Take your hand right now. Pick up an imaginary grain of sand between your thumb and forefinger. Hold it out at arm's length. Look up at the sky. That tiny speck, that minuscule point blocking your view, that grain of sand covers a patch of sky that contains almost 800,000 galaxies. Not stars. Galaxies. Each one containing billions or trillions of stars. Each one an entire universe unto itself. This is what the Cosmos Webb survey revealed after James Webb spent over 200 hours staring at one single patch of space, refusing to look away, gathering every photon it could detect from that region. 200 hours of continuous observation focused on an area covering just 0.6 square degrees of sky. To put that in perspective, the full moon as you see it from Earth covers about 0.2 degrees. The Cosmos Webb survey examined an area roughly 3 times the size of the full moon. In cosmic terms, this is microscopic. It's a tiny sliver of the visible universe, a pinprick, barely anything at all. The entire sky contains over 40,000 square degrees. The Cosmos Webb survey looked at 0.6 of them. That's less than 1/100% of the total available sky. A fraction so small it barely registers. Yet within that tiny sliver, James Webb found more galaxies than most human minds can properly comprehend. 800,000 galaxies. Each one existing at a different distance, meaning we're seeing them at different times in cosmic history. Some are relatively nearby, showing us what galaxies looked like just a few billion years ago. Others are so distant their light left them over 13 billion years in the past, when the universe was barely out of its infancy. The survey essentially created a timeline of the entire cosmic history, all visible in one composite image. Nearby galaxies show the present or recent past. Mid-distance galaxies show the universe a few billion years ago. The most distant galaxies show the cosmic dawn, that period when the first stars and galaxies were forming, when light was just beginning to flood into the darkness. The Cosmos Webb project used both of James Webb's primary infrared instruments to capture this data. Astronomers deliberately chose this particular field in the sky because it has very few foreground stars or gas clouds blocking the view. Looking through our Milky Way galaxy is like trying to see through fog. Stars and dust in our own galaxy obstruct our view of distant objects. The cosmos field is like a clear window, a region where we can see deep into space with minimal interference. This field has been observed by multiple telescopes over the years. Hubble looked at it. Ground-based observatories studied it. Each telescope added to our knowledge of this region. But James Webb's infrared sensitivity allowed it to see galaxies that Hubble missed entirely, galaxies so distant their visible light had been stretched completely into infrared wavelengths invisible to Hubble's instruments. What makes the Cosmos Webb survey revolutionary is its combination of width and depth. Many deep field images focus on extremely small areas, tiny patches of sky barely larger than a pinpoint. These ultra-deep fields maximize observation time, staring at one spot for hundreds of hours to detect the faintest possible objects. They go incredibly deep but cover almost no area. Other surveys go wide, mapping large portions of sky but without much depth. They can show you where galaxies are distributed across large regions but don't see the faintest, most distant objects. You get breadth but not depth. Cosmos Webb strikes a balance between these extremes. It sacrificed some depth compared to the deepest possible observations in order to cover a larger area. The result is a map showing how galaxies are distributed across billions of light-years of space. You can see galactic structures, clusters of galaxies grouped together by gravity, vast voids where almost no galaxies exist, filaments of galaxies stretching across space like cosmic highways connecting the clusters. The image shows galaxies at every stage of evolution. Spiral galaxies with elegant arms sweeping out from their cores, looking like cosmic pinwheels frozen in time. Elliptical galaxies that are smooth and featureless, bloated spheres of old stars that have settled into stable configurations. Irregular galaxies twisted by gravitational interactions, their shapes distorted, chaotic, showing the scars of violent encounters with neighbors. Scattered throughout the image are galaxies in the process of merging. You can see them colliding, their structures warped as gravity tears them apart and pulls them together simultaneously. Stars from one galaxy mixing with stars from another. Gas clouds colliding, triggering massive bursts of star formation. Two galaxies becoming one, a process that takes hundreds of millions of years captured in a single frozen moment. Everywhere in this image, scattered like embers from the cosmic dawn, are little red dots. Those mysterious objects we talked about earlier, galaxies from the early universe with their impossibly massive black holes, their compact sizes, their extreme brightness. They're not rare anomalies. They're everywhere, peppered throughout the first billion years of cosmic history. One of the most unexpected findings from Cosmos Webb is the sheer number of early galaxies. Before James Webb, computer models predicted far fewer bright galaxies should exist in the first billion years after the Big Bang. The early universe should have been relatively empty, with just a handful of small proto-galaxies beginning to form, nothing particularly bright or massive yet. The Cosmos Webb survey found 10 times more bright early galaxies than models predicted. 10 times. Not slightly more, not a bit higher than expected. An order of magnitude more. This suggests galaxy formation in the early universe was far more efficient than our theories predicted. Stars formed faster. Galaxies assembled quicker. The process of building massive stellar populations happened more rapidly than we thought possible. The early universe was not empty and quiet, slowly ramping up its activity over billions of years. It was crowded and active right from the start, bursting with galaxy formation, filled with young stellar populations blazing away in the cosmic dawn. The survey also revealed large-scale structures forming earlier than anticipated. Galaxy groups and clusters that should have taken longer to assemble through gravitational attraction are already visible in the early universe. Gravity was pulling galaxies together faster than models suggested. Individual galaxies were finding each other, clustering together, beginning to form the cosmic web structure we see in the modern universe. The cosmic web is the large-scale structure of the universe, the way galaxies are distributed across space. They're not scattered randomly. They form filaments, long chains stretching across hundreds of millions of light-years. These filaments connect massive clusters where hundreds or thousands of galaxies crowd together. Between the filaments are vast voids, enormous empty regions containing almost no galaxies at all. This web-like structure was thought to take billions of years to develop, slowly emerging as gravity pulled matter together over cosmic time. Cosmos Webb shows the structure was already taking shape when the universe was just a few billion years old. The filaments existed. The clusters were forming. The voids were already apparent. The cosmic web assembled itself much faster than we expected. Each galaxy in the Cosmos Webb image has its own story, its own history spanning billions of years. Each formed through a unique combination of dark matter providing gravitational scaffolding, gas clouds collapsing under gravity, stars igniting and flooding their surroundings with energy. Some galaxies experienced violent mergers early in their history, growing large through collisions and cannibalism. Others grew quietly over billions of years, accumulating mass slowly through steady star formation. Some galaxies in the image are actively forming stars right now as we observe them. Their light shows the characteristic glow of young, hot stellar populations, massive blue stars burning fiercely. Other galaxies are old and dead, their star formation shut down billions of years ago. Their stars have long since burned out or evolved into faint red dwarfs. These dead galaxies shine with a ghostly light, echoes of past activity, fossils from an earlier epoch. The Cosmos Webb survey will be studied for years, probably decades. Astronomers will analyze individual galaxies, measuring their distances precisely, studying their compositions, tracking how their properties change over cosmic time. Every new analysis will refine our understanding of how galaxies evolve. Every discovery will add another piece to the enormous puzzle of cosmic evolution, helping us understand how the universe grew from the Big Bang's initial fireball into the structured, galaxy-filled cosmos we inhabit today. This is just one patch of sky. One tiny region containing 800,000 galaxies. There are over 40,000 square degrees across the entire celestial sphere. If every patch of sky contains this density of galaxies, if every region reveals this many objects when examined with sufficient care, the total number of galaxies in the observable universe exceeds 2 trillion. 2 trillion galaxies. The number is so large it loses meaning. Human brains can't visualize 2 trillion of anything. We can barely comprehend a million. A billion stretches our imagination to its limits. 2 trillion is just a symbol, a mathematical abstraction representing the universe's incomprehensible vastness. Each galaxy containing billions or trillions of stars. Each star potentially hosting planets. The numbers multiply into scales that make our minds simply give up trying to grasp the totality. Among those 2 trillion galaxies, one black hole is doing something unprecedented. It's running away. Imagine something weighing 10 million times more than the Sun. Now imagine it running, fleeing through space, terrified. Black holes don't move around much in the grand scheme of things. They sit at the centers of galaxies, anchored there by gravity, spinning in place while everything else orbits around them. They're the gravitational anchors holding entire galaxies together, the stable centers around which billions of stars revolve. They don't wander. They don't travel. They certainly don't flee. Except one of them is fleeing right now. Racing through space at 2 million miles per hour. This black hole weighs 10 million times what our Sun weighs. That's supermassive by any measure, a genuine cosmic monster. Yet something kicked it out of its home galaxy with enough force to send it rocketing through intergalactic space at 3,000 times the speed of sound. It's not orbiting anything. It's not falling toward anything. It's running, ejected from its galaxy like a bullet fired from a gun, traveling so fast it will eventually escape the galaxy system entirely and wander through the vast empty spaces between galaxy clusters as a rogue object, homeless and alone. James Webb confirmed this discovery in 2025, making it the first verified runaway supermassive black hole ever observed. The object sits in a galaxy system called the Cosmic Owl, which isn't actually a single galaxy at all. It's multiple galaxies caught in the violent process of merging, colliding together, their structures torn apart by tidal forces, their stars mixing, their gas clouds smashing together. When galaxies collide, their central black holes eventually sink toward the center of the merged system. Gravity pulls them inward through a process called dynamical friction. The black holes interact with surrounding stars and gas, losing energy with each interaction, spiraling slowly toward the core of the newly forming galaxy. Usually, they end up orbiting each other at the center, eventually merging together after millions of years of this gravitational dance. But in rare cases, something goes catastrophically wrong. Gravitational interactions during the merger can eject one of the black holes entirely, flinging it out into space like a stone from a slingshot. That's what happened here in the Cosmic Owl system. One black hole got kicked out, sent flying, banished from the galaxy it once called home. There are 2 ways to kick a supermassive black hole out of a galaxy with enough force to make it flee at these speeds. Both involve extreme physics, events so violent they barely seem possible. The first method involves the merger of 2 supermassive black holes. When 2 black holes spiral together and finally merge, they don't just combine their masses peacefully. The merger produces gravitational waves, ripples in spacetime itself that carry away enormous amounts of energy. These waves don't necessarily radiate symmetrically in all directions. If the black holes have different masses or different spins, if they're oriented at particular angles when they merge, the gravitational waves can be emitted preferentially in certain directions. This asymmetric emission creates recoil, momentum in one direction that pushes the merged black hole in the opposite direction. It's exactly like the recoil from firing a gun. The bullet goes forward, the gun kicks backward. When black holes merge and their gravitational waves shoot out asymmetrically, the resulting merged black hole gets kicked in the opposite direction. The velocities from these gravitational recoil events can be tremendous, reaching thousands of miles per second. That's more than enough to exceed the escape velocity of even a massive galaxy. The merged black hole rockets away, leaving its former home behind, traveling so fast that gravity can't pull it back. The second method involves a three-body interaction. Suppose a galaxy already had two supermassive black holes at its center, perhaps from a previous merger that hadn't yet completed. The two black holes were orbiting each other in a binary pair, spiraling slowly inward. Then a third galaxy merged with the system, bringing its own central black hole into the mix. Now you have three supermassive black holes interacting gravitationally. This creates what physicists call a three-body problem. Two bodies orbiting each other are stable and predictable. Their motions can be calculated precisely. But add a third body and the system becomes chaotic, unpredictable, unstable. The gravitational interactions become impossibly complex. In these chaotic three-body encounters, one black hole almost always gets ejected. The other two remain bound together while the third gets slingshot out at high speed, carrying away energy and angular momentum from the system. It's not a question of if one gets ejected but which one. The dynamics are unstable enough that one black hole always loses the gravitational tug-of-war and gets thrown out. James Webb detected this runaway black hole through an indirect signature. The black hole itself is invisible, as all black holes are unless they're actively feeding on matter. But as it plows through the thin gas that fills intergalactic space at 2 million miles per hour, it creates a bow shock ahead of itself, exactly like a boat moving through water creates a wake. The black hole's tremendous speed compresses the gas in front of it. This compressed gas heats up from the compression, glowing with thermal radiation that James Webb can detect. The telescope saw this bow shock, this glowing region of compressed gas shaped like a crescent or arc ahead of the black hole's position. The shape and brightness of the shock wave allowed astronomers to calculate how fast the black hole was moving. Behind the black hole, stretching back along its path like a contrail behind a jet aircraft, lies something even more remarkable. A trail of newborn stars 200,000 light-years long. 200,000 light-years. That's longer than the entire diameter of our Milky Way galaxy. The black hole's passage has triggered star formation along its entire path, creating a stream of young stars marking where it's been. This is completely unprecedented. Stars forming in the wake of a runaway black hole, left behind like breadcrumbs marking the monster's escape route. Here's how this works. As the black hole races through intergalactic space, its gravity affects the gas around it even though the black hole itself isn't feeding. The gravitational field pulls on nearby gas, compressing it, increasing its density. In the wake behind the black hole, after it passes, this compressed gas becomes dense enough to collapse under its own gravity. Gas clouds that were too diffuse to form stars before the black hole passed through them suddenly find themselves compressed just enough to tip over the edge into gravitational collapse. They fragment. They condense. Temperatures rise in their cores. Nuclear fusion ignites. New stars are born, not because the black hole wanted to create them, but as an accidental consequence of its passage through space. These young stars are bright because young stars always are. They shine in ultraviolet and visible light, pumping out tremendous amounts of energy. That light gets stretched during its journey to us, redshifted into infrared wavelengths by the time it reaches James Webb's detectors. The telescope sees this long filament of infrared light marking the trail, a glowing path through space showing exactly where the runaway black hole has been. The speed is genuinely mind-boggling when you try to picture it in terms we can understand. 2 million miles per hour. In 1 second, this black hole travels over 500 miles. It crosses the distance from Earth to the Moon in less than 2 minutes. At this rate, it would cross the entire solar system in just a few hours. This black hole is moving so fast that it will definitely escape the cosmic owl galaxy system entirely. The escape velocity, the speed needed to break free from the system's gravitational pull, is far less than 2 million miles per hour. Nothing is going to slow this black hole down or turn it around. It's gone, banished to intergalactic space, destined to wander through the enormous voids between galaxy clusters as a rogue object. Galaxies without central black holes are extremely rare in the modern universe. Nearly every large galaxy contains a supermassive black hole at its core. It's one of the fundamental features of galaxy structure. But the cosmic owl system is about to become one of those rare exceptions, missing its central black hole because it got kicked out during a merger gone wrong. What does this discovery mean for our understanding of how black holes evolve? Runaway black holes were predicted by computer simulations years ago. Theorists calculated that gravitational recoil and three-body interactions should sometimes eject black holes during galaxy mergers. But finding one in reality confirms they actually exist. Theory became observation. Prediction became confirmation. It also raises questions about how common these events might be. If galaxy mergers frequently eject black holes, if this isn't an extremely rare occurrence but something that happens regularly when galaxies collide, there could be thousands of rogue black holes drifting through intergalactic space right now. Most would be invisible because they're no longer feeding on matter. They'd be dark, silent, undetectable except through their gravitational effects on surrounding gas or stars. The discovery also suggests that black hole mergers in the early universe, during the cosmic dawn when galaxies were colliding more frequently, may have been incredibly chaotic and violent. As young galaxies formed and collided, their black holes would have interacted in complex ways. Some merged successfully, combining their masses. Others got ejected, kicked out into space. The process was messy, unpredictable, violent. Black holes scattered across the cosmos, some growing through mergers, others ejected and left to wander alone. The final distribution of black holes we see today, with one supermassive black hole at the center of most large galaxies, emerged from this chaotic process of collisions, mergers, and ejections. James Webb's ability to detect this runaway black hole demonstrates just how sensitive the telescope is to faint structures. The bow shock and star trail aren't bright. They required long exposure times to capture, careful analysis to identify, sophisticated techniques to separate from background noise. Yet they revealed something nobody had seen before, a supermassive black hole in full retreat, racing away from its home galaxy, leaving a trail of creation in its wake. Not all black holes are running away. Some are rushing toward each other in the most violent collision the universe can produce. Two monsters are dancing. Getting closer every moment. When they finally touch, spacetime itself will scream. Deep in the early universe, 740 million years after the Big Bang, two supermassive black holes are locked in a death spiral. They're circling each other, orbiting faster and faster, drawing closer with every revolution. Eventually, inevitably, they will collide. When that happens, the merger will release more energy in a fraction of a second than all the stars in the visible universe combined produce over their entire lifetimes. This is happening in a galaxy system designated JWST. James Webb detected this cosmic catastrophe in the making by analyzing the spectrum of light coming from the system. The data showed not one but two distinct sources of energetic radiation positioned very close together. Both sources displayed the unmistakable signatures of actively feeding black holes, fast-moving gas spiraling inward, atoms stripped of their electrons by intense radiation, broad emission lines indicating material orbiting at tremendous velocities. The two black holes are separated by only a few thousand light-years right now. In cosmic terms, that's nothing. That's like two people standing in the same room. They're practically on top of each other. Measurements show they're moving toward one another, their orbital separation shrinking, the gap between them closing. This is the most distant black hole merger ever detected. It's also the earliest in cosmic time. Previous black hole mergers have been observed in the modern universe, relatively nearby events where we could study the process in detail. But never this far back, never this early in the universe's history. The discovery confirms that black holes were already colliding and merging when the cosmos was less than 1 billion years old. This has enormous implications for understanding how supermassive black holes grew so large so quickly in the early universe. Mergers are one of the fastest ways to build massive black holes. Instead of slowly accumulating mass by consuming gas over millions of years, two black holes can combine their masses in a single violent event. 1 + 1 = 1 bigger black hole, instantly doubling the mass. If mergers were common during the cosmic dawn, if black holes were regularly finding each other and combining, it could explain how some black holes reached billions of solar masses within the first billion years after the Big Bang. Each merger represents a quantum leap in mass, a shortcut past the slow process of gas accretion. The merger process itself is fascinating from a physics standpoint. As two black holes orbit each other, they emit gravitational waves. These are ripples in the fabric of spacetime itself, predicted by Einstein's general theory of relativity over a century ago but only detected directly in recent years by instruments on Earth. Gravitational waves carry energy away from the system. Every wave that ripples outward represents energy leaving the binary black hole pair. As energy leaves, the orbit decays. The black holes spiral closer together. As they get closer, they orbit faster. As they orbit faster, they emit stronger gravitational waves. The waves carry away more energy. The orbit decays faster. It's a runaway process, a feedback loop that accelerates over time. In the early stages, when the black holes are separated by thousands of light-years, the orbital decay is slow. Gravitational wave emission is weak. The black holes might orbit each other for millions of years with barely any change in their separation. But as they spiral inward, crossing thresholds of distance, the process accelerates dramatically. By the time the black holes are separated by just a few light-years, orbiting each other every few thousand years, the gravitational wave emission becomes significant. The orbit decays faster, the period shortens, the black holes draw even closer. When they're separated by mere light months, orbiting every few years, the process enters its final phase. The last moments happen incredibly quickly. The black holes spiral together over a matter of hours, then minutes, then seconds. They're orbiting each other multiple times per second, moving at significant fractions of the speed of light, whipping around each other in an insane gravitational dance. The gravitational waves they're emitting are tremendously powerful, carrying away solar masses worth of energy every second. Finally, they touch. The event horizons merge. The collision happens in a fraction of a second, releasing more energy in gravitational waves than all the stars in the entire visible universe emit as light during their lifetimes. The spacetime around the merger vibrates like a bell that's been struck, ringing with gravitational waves that propagate outward at the speed of light, spreading across the cosmos. We cannot detect the gravitational waves from JWST with current technology here on Earth. The waves are too faint after traveling over 13 billion light-years to reach us. Gravitational wave detectors on Earth like LIGO and Virgo are sensitive to waves from stellar mass black hole mergers happening relatively nearby, within a few billion light-years. But they're not sensitive enough to detect waves from supermassive black hole mergers at cosmological distances. That will change in the coming decades. A space-based gravitational wave observatory called LISA, the Laser Interferometer Space Antenna, is scheduled to launch in the 2030s. LISA is specifically designed to detect gravitational waves from supermassive black hole mergers. It will observe these events routinely, watching black holes collide throughout the universe, measuring the waves they produce, extracting information about their masses, spins, and orbital dynamics. When LISA becomes operational, it will detect mergers like JWST happening throughout cosmic history. The observatory will open a completely new window on the universe, allowing us to witness black hole collisions not through light but through the gravitational waves they generate, the ripples in spacetime itself. What makes the JWST discovery so critical is that it provides a preview of what LISA will observe. Before James Webb found mergers happening in the early universe, scientists thought events like this would be relatively rare. The models predicted that supermassive black hole mergers should be uncommon during the cosmic dawn because galaxies were still forming, black holes were still small, the conditions for mergers weren't ideal yet. Now we know those predictions were wrong. Mergers were happening. Black holes were colliding and combining. The rate of mergers in the infant universe was much higher than models suggested. This means LISA will detect far more gravitational wave events than astronomers initially predicted. The universe was more violent, more merger-prone during its youth than we realized. The merger also tells us important things about galaxy evolution. JWST formed from two smaller galaxies colliding and beginning to merge. As the galaxies combine, their stars mix together, their gas clouds collide and trigger bursts of star formation, their dark matter halos blend into one larger halo. The galaxies are becoming a single merged system. As this happens, the central black holes from each galaxy sink toward the center of the newly forming combined galaxy through dynamical friction. They interact with stars and gas, losing orbital energy with each interaction, spiraling inward over millions of years. Eventually they form a binary pair orbiting each other at the core of the merged galaxy. Given enough time, that binary will shrink until the black holes finally merge. This same sequence happens throughout cosmic history whenever galaxies collide. It's still happening today in the modern universe. Our own Milky Way galaxy is currently on a collision course with the Andromeda galaxy. The two galaxies are approaching each other at over 200,000 miles per hour. In about 4 billion years, they will collide. When that collision happens, our Sun and solar system will likely be flung to a different part of the merged galaxy, thrown into a new orbit by gravitational interactions during the merger. The night sky will look completely different as we move to a new location within the combined galaxy. Stars from Andromeda will mix with stars from the Milky Way. Gas clouds will collide, triggering massive bursts of new star formation. The supermassive black holes at the centers of both galaxies, the one at the Milky Way's core weighing 4 million solar masses and the one at Andromeda's core weighing perhaps 20 times more, will eventually sink toward the center of the merged system. They'll form a binary pair. They'll spiral together over millions of years. Eventually, billions of years from now, they'll merge in an explosion of gravitational waves. The process we're seeing in JWST is the same process that will happen to our own galaxy in the distant future. We're watching our cosmic destiny play out in a galaxy so far away its light has been traveling for over 13 billion years to reach us. The gravitational waves from the JWST merger were emitted 13 billion years ago. They've been traveling through space ever since, stretching as the universe expanded, their wavelengths lengthening, their frequencies dropping. By the time LISA detects them decades from now, they will have been transformed into long wavelength signals that require space-based detectors to observe. Those waves carry information encoded in their patterns, in their amplitude and frequency evolution. They contain details about the masses of the black holes that merged, how fast they were spinning, the dynamics of their final plunge, the properties of the merged black hole left behind. Future astronomers will decode that information, extracting knowledge that James Webb cannot see, learning things about these black holes that optical and infrared telescopes simply cannot reveal. While black holes are merging and creating monsters, some galaxies are doing something equally impossible with stars. Imagine a factory producing hundreds, maybe thousands of new stars every single year. That's what's happening right now. Star formation takes time. You need a cloud of hydrogen gas floating in space. Gravity starts pulling that cloud together, compressing it slowly. The cloud fragments into smaller clumps. Each clump continues collapsing under its own gravity. As it collapses, it heats up from the compression. The temperature climbs higher and higher. Eventually, when the core reaches about 10 million degrees, nuclear fusion ignites. Hydrogen atoms start fusing into helium. Energy floods outward. A star is born. This process from start to finish takes millions of years minimum. The initial collapse is slow. The fragmentation takes time. The heating happens gradually. Nature doesn't rush star formation. It's a patient, methodical process that unfolds over enormous timescales. In the modern universe, galaxies form stars at relatively leisurely rates. Our Milky Way creates about 3 new stars per year on average. Some years it might make 5, other years just 1, but averaging out over millions of years, it's around 3 per year. That might sound fast until you realize our galaxy contains somewhere between 200 and 400 billion existing stars. The formation rate is tiny compared to the total stellar population. This slow rate is typical for mature galaxies like ours. Most of the available gas has already been converted into stars over billions of years of previous star formation. What's left is either too hot or too diffuse to collapse easily. Stellar winds from existing stars and explosions from supernovas blow gas out of the galaxy or heat it up, making it harder for new stars to form. The galaxy has settled into a relatively quiet state where star formation continues but at a reduced pace. Then there's a galaxy called JWST 140. It existed just 290 million years after the Big Bang. James Webb measured its brightness, analyzed its spectrum, calculated its properties. When astronomers worked out how fast this galaxy was forming stars, when they did the math and checked their results, they couldn't believe the numbers. The galaxy is creating new stellar mass equivalent to hundreds or possibly thousands of stars per year. The exact number depends on assumptions about stellar masses, but even conservative estimates put it at over 100 times faster than our Milky Way. For a galaxy that young, that small, that early in cosmic history, this rate is absolutely insane. It means the entire galaxy is functioning as a giant star-forming furnace with gas clouds collapsing simultaneously across its entire volume. Think about what this requires. You need massive amounts of gas available for star formation. You need that gas to be cool enough and dense enough to collapse efficiently. You need continuous resupply as existing gas gets converted into stars. You need conditions that favor collapse rather than preventing it. Star formation in any galaxy faces natural limits. When stars form, they don't just sit there quietly. Young stars produce intense radiation that heats surrounding gas, making it harder for additional stars to form. Massive stars have powerful stellar winds that blow gas away. When the most massive stars run out of fuel and explode as supernovas, they inject tremendous energy into their surroundings, disrupting nearby gas clouds, preventing them from collapsing. These feedback mechanisms naturally slow down star formation. A galaxy can't just keep cranking out stars indefinitely at maximum rate because the stars themselves interfere with the process. The system self-regulates, reaching an equilibrium where star formation continues but at a rate balanced against stellar feedback. JWST 140 apparently didn't get that memo. It's forming stars at a rate that suggests feedback mechanisms either aren't working yet or are overwhelmed by the sheer amount of gas available. The galaxy is going through what astronomers call a starburst, an episode of extremely rapid star formation far exceeding normal rates. Why is this happening? One theory involves cold gas streams. In the early universe, gas was distributed differently than it is today. Dark matter formed invisible scaffolding, creating gravitational wells where normal matter could accumulate. Gas flowed along filaments connecting these dark matter halos, streaming into young galaxies like rivers feeding a lake. These cold gas streams could provide a constant supply of fresh material for star formation. As fast as the galaxy converts gas into stars, more gas flows in from outside, replenishing the supply. The galaxy never runs out of raw material. It just keeps forming stars continuously, fed by these cosmic rivers of gas. Another possibility is that JWST 140 recently experienced a merger with another galaxy. When two galaxies collide, their gas clouds smash together. This collision compresses the gas dramatically, triggering massive bursts of star formation throughout both galaxies. The collision acts like squeezing a sponge, forcing gas to collapse everywhere at once. Star formation rates during galaxy mergers can spike by factors of 10 or more compared to normal rates. The burst typically lasts for a few 100 million years before settling back down as the merger completes and the combined galaxy relaxes into a more stable configuration. JWST might be caught in the middle of such a merger-driven starburst, showing us what happens when two young galaxies collide during the cosmic dawn. The brightness of this galaxy is another mystery layered on top of the star formation puzzle. Young stars are hot and luminous. The most massive young stars burn with tremendous intensity, pumping out enormous amounts of ultraviolet light. This ultraviolet radiation heats surrounding gas, causing it to glow. The combination of stellar light and glowing gas makes star-forming galaxies bright. JWST is brighter than expected, even accounting for its extreme star formation rate. The light output suggests either the stars being formed are unusually massive compared to typical stellar populations, or there's another energy source contributing to the brightness beyond just normal stars. Some astronomers think supermassive stars might be involved. These hypothetical objects would weigh hundreds of times more than typical stars, perhaps even thousands of solar masses. They would burn incredibly hot, shining with tremendous luminosity, living only a few million years before exploding. No confirmed observations of supermassive stars exist, but if JWST managed to form a population of them, their combined light would easily explain the excessive brightness. The problem is that supermassive stars remain purely theoretical. We don't know if they can actually form, under what conditions they might arise, how common or rare they might be. Computer simulations suggest they could exist under certain circumstances in the early universe, but simulations aren't proof. We need observations. JWST might be providing indirect evidence, but it's not conclusive yet. The galaxy's spectrum shows strong emission lines from oxygen and hydrogen. These lines confirm active star formation is happening. The specific pattern and strength of the lines tell astronomers that massive amounts of gas are being ionized by ultraviolet radiation from young stars. The lines are broader than normal, suggesting the gas is turbulent, moving at high speeds, churning violently. This turbulence might be driven by stellar winds and supernova explosions. Young massive stars die quickly, living only a few million years before exploding. Each explosion injects energy into surrounding gas, stirring it up, creating chaotic motion. In a galaxy forming stars as rapidly as JWST, supernovas would be going off constantly, multiple explosions per year, each one adding to the turbulence. What really bothers scientists is the compressed timescale. At 290 million years after the Big Bang, the universe barely had time to form the first generation of stars, let alone build a massive star-forming galaxy operating at full capacity. According to our models, JWST should be in its infancy, just beginning to pull together its first significant stellar population. Instead, it's fully active, mature beyond its years, producing stars at a breakneck pace that modern galaxies would struggle to match. This suggests galaxy formation was fundamentally more efficient in the early universe than current models predict. Gas collapsed faster back then. Maybe it was colder on average, making collapse easier. Maybe turbulence was lower, allowing smooth collapse instead of fragmented chaotic collapse. Maybe dark matter halos were configured differently, creating stronger gravitational wells that pulled gas together more effectively. Stars formed quicker once gas clouds began collapsing. Maybe the gas was more pristine, lacking heavy elements that normally cool gas and slow down collapse. Maybe feedback mechanisms that shut down star formation in modern galaxies were weaker or absent in the early universe. Maybe radiation pressure from stars didn't disrupt nearby gas clouds as effectively. The early cosmos was apparently a more productive, more efficient environment for building galaxies and forming stars. Processes that take billions of years in the modern universe happened in hundreds of millions of years back then. Everything was accelerated, compressed, happening faster. Every discovery like JWST forces astronomers to go back to their theoretical models and adjust the parameters. The numbers get revised. The timescales get compressed. The efficiency factors get increased. The picture of the early universe becomes more chaotic, more violent, more productive, more impressive than previous generations of astronomers imagined. We thought we understood how galaxies formed. We built detailed computer simulations that tracked gas dynamics, star formation, feedback processes, dark matter evolution. Those simulations produced galaxies that looked reasonably similar to what we observe in the modern universe. We thought we had it figured out. Then James Webb started looking at the actual early universe rather than simulated versions. It found galaxies forming stars faster than simulations predicted. It found galaxies appearing earlier than models said they should. It found structures assembling on timescales that seemed impossibly short. The real universe during the cosmic dawn was wilder, faster, more intense than our best theoretical models captured. We were close but not quite right. The details matter. The discrepancies are telling us something important about physics we don't fully understand yet, about conditions in the early universe that differed from our assumptions. All these discoveries raise a fundamental question: do we really understand how fast the universe is expanding? Something is wrong. Two measurements, both careful, both precise, giving two different answers. James Webb just confirmed the problem is real. The universe is expanding. We've known this since the 1920s when astronomer Edwin Hubble discovered that distant galaxies are moving away from us. The farther away a galaxy is, the faster it's receding. This expansion isn't happening because galaxies are moving through space like cars on a highway. Space itself is growing, stretching, getting larger. The galaxies are embedded in that space, carried along by its expansion like raisins in rising bread dough. Understanding exactly how fast the universe is expanding is one of the most fundamental questions in all of cosmology. The expansion rate tells us the age of the universe, its ultimate fate, the nature of the mysterious dark energy driving the acceleration. Getting this number right matters enormously for our understanding of cosmic history and the laws of physics governing reality itself. The expansion rate is measured by something called the Hubble constant. This number tells us how fast galaxies are moving away from us at a given distance. The current estimates put it around 70 kilometers per second per megaparsec. That sounds complicated, but here's what it means in plain language. A megaparsec is a distance unit equal to about 3.3 million light-years. So if the Hubble constant is 70, a galaxy located 1 megaparsec away is receding from us at 70 kilometers per second. A galaxy 2 megaparsecs away is receding at 140 kilometers per second. The farther away something is, the faster it's moving away, with the speed proportional to distance. For decades, astronomers have been trying to measure this constant as precisely as possible. You'd think this would be straightforward. Measure the distances to galaxies. Measure how fast they're moving away. Divide speed by distance. Get the Hubble constant. Done. Except it's not done. It's not straightforward at all. Because there are two main ways to measure the Hubble constant, two completely different methods using different data and different techniques. Both methods are carefully designed. Both have been checked and rechecked countless times. Both are precise and reliable. And they give different answers. The first method uses observations of the cosmic microwave background, often abbreviated CMB. This is the faint glow left over from the Big Bang itself, radiation that fills the entire universe. When you look at the CMB, you're seeing light that was released 380,000 years after the Big Bang, when the universe first became transparent. The CMB isn't perfectly uniform. It has tiny temperature variations, spots that are slightly hotter or colder than average. These variations are incredibly small, just a few millionths of a degree, but they carry enormous amounts of information about the early universe. The pattern of these temperature fluctuations tells us about the density of matter, the amount of dark matter and dark energy, how fast the universe was expanding back then. By analyzing these tiny variations carefully, using sophisticated mathematical models and enormous amounts of computing power, scientists can calculate how fast the universe was expanding 380,000 years after the Big Bang. They can then use our best theoretical models of cosmic evolution to project forward to the present day, calculating what the expansion rate should be now. This method gives a Hubble constant of about 67 kilometers per second per megaparsec. The second method uses observations of nearby stars and galaxies. Astronomers measure distances to galaxies using objects called Cepheid variable stars. These are special stars that pulsate, brightening and dimming in a regular cycle. The period of pulsation is directly related to the star's intrinsic brightness. By measuring how long the pulsation cycle takes, you know how bright the star actually is. By comparing that to how bright it appears from Earth, you can calculate exactly how far away it is. Once you know the distance to a galaxy containing Cepheid variables, you can use that galaxy to calibrate other distance indicators like type Ia supernovas. These exploding stars are bright enough to be seen across enormous distances. By building up a ladder of distance measurements, from nearby Cepheids to distant supernovas, astronomers can measure how fast galaxies at various distances are receding. This method measures the expansion rate directly in the local universe, within a few billion light-years of Earth. It doesn't rely on theoretical models of cosmic evolution. It's a direct measurement based on actual observations of real objects. This method gives a Hubble constant of about 73 kilometers per second per megaparsec. 67 versus 73. A difference of 6. That might not sound like much, but in precision cosmology, it's enormous. It's not a rounding error. It's not measurement uncertainty. It's not a small systematic effect that could be corrected. Both methods are precise. Both have been refined over decades of work. Both have tiny error bars showing they're measuring their respective values accurately. The discrepancy is real. It's persisted for over a decade now. It's gotten stronger and more significant as measurements improved rather than going away as you'd expect from random errors. Astronomers call this problem the Hubble tension, and it's one of the biggest mysteries in modern cosmology. For years, there was a hope that maybe the problem lay with measurement errors. Maybe the Hubble Space Telescope observations of Cepheid variable stars had some systematic bias nobody had noticed. Maybe the distance measurements were slightly off. Maybe there was some subtle effect skewing the results. This is where James Webb enters the story. Webb can observe Cepheid variable stars with better sensitivity and resolution than Hubble. If Hubble's measurements were flawed somehow, Webb would find different values. The distances would change. The Hubble constant calculated from local measurements would shift, hopefully moving closer to the value from the cosmic microwave background. Webb observed the same Cepheid variables Hubble had studied. It measured their brightness carefully, calculated their distances precisely. When the results came back, when scientists compared Webb's measurements to Hubble's earlier work, they found something both reassuring and deeply troubling. The measurements matched. Webb confirmed Hubble's observations. The distances were correct. The expansion rate measured using nearby objects really is about 73. The tension is not due to observational errors. It's real. This leaves us with a profound problem. Either our model of how the universe evolves is incomplete, missing some crucial piece, or something changed in how the universe expands over cosmic time. The standard model of cosmology assumes the expansion rate follows a smooth, predictable pattern determined by the amounts of matter, and dark energy in the universe. If you know those quantities and how they interact, you can calculate how the expansion rate changes over time. The model has worked remarkably well, explaining countless observations, making successful predictions about galaxy distributions, cosmic structure formation, the evolution of the universe. But if the model's assumptions are wrong, if something about it is incomplete or incorrect, the predictions break down. The discrepancy between cosmic microwave background measurements and local measurements could be telling us that the standard model needs revision. One possibility involves dark energy, the mysterious force causing the universe's expansion to accelerate. We know dark energy exists because we observe the acceleration. But we don't know what it actually is. We just know it's there, making up about 68% of the universe's total energy budget. The standard model assumes dark energy has constant density throughout space and time. But what if that's wrong? What if dark energy's strength changed over cosmic history? Maybe it was weaker in the early universe, making expansion slower back then. Maybe it's stronger now, making current expansion faster. This changing strength could explain why measurements from different cosmic epochs give different results. Another possibility is that there's some unknown component to the universe we haven't detected yet. Some new form of energy or matter that affects expansion but hasn't shown up in our observations so far. This would be a major discovery, equivalent to finding a missing ingredient in the recipe for the cosmos, something fundamental we've overlooked. Perhaps the problem lies with how we interpret the cosmic microwave background data. The analysis relies on complex models of the early universe. If those models are wrong in some subtle way, if the early universe was different than we assume, the projections to the present day would be incorrect. Maybe structure formed differently than we think. Maybe dark matter behaved differently. Maybe something about the physics of the early universe differs from our current understanding. The Hubble tension represents a crack in the foundation of modern cosmology. It suggests our understanding is incomplete. Something is missing. Something we haven't accounted for. Until we figure out what that something is, until we understand why two careful measurements give different answers, the tension will remain. This isn't just an academic puzzle for specialists to argue about in journals. The Hubble constant determines fundamental things like the age of the universe, the distances to faraway objects, the timeline of cosmic evolution. Getting it wrong means our cosmic timeline is wrong, our distance scales are wrong, our understanding of when things happened is wrong. James Webb's confirmation that the tension is real, that it's not just measurement error, moves the problem from maybe we made a mistake to something is genuinely wrong with our models. This is simultaneously exciting and unsettling. Exciting because it means there's new physics to discover, new phenomena to understand. Unsettling because it means our cosmic model, which has worked so well for so long, has a serious flaw we need to identify and fix. To solve these cosmic mysteries, we need to look even further back, to the very first stars that ever existed. There's a type of star nobody has ever seen. They lived fast, died young, and created everything we're made of. Every atom in your body except hydrogen was created inside a star. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood. None of these elements existed when the universe began. They were forged in the nuclear furnaces at the cores of stars, then scattered into space when those stars exploded as supernovas. Stars are divided into different populations based on their chemical composition. Astronomers use the term metals to mean anything heavier than helium. Iron is a metal. Carbon is a metal. Oxygen, nitrogen, silicon, all metals in astronomy terminology. This classification might seem strange, but it's useful for categorizing stars by their age and formation history. Modern stars like our Sun are called population 1 stars. They contain a few percent metals by mass. These are young stars formed from gas clouds that had already been enriched by previous generations of stellar explosions. The metals in these stars came from ancient supernovas that died long ago, seeding the galaxy with heavy elements. Older stars found in globular clusters and the outer reaches of galaxies are called population 2 stars. They contain much less metal, maybe 0.1% or less. These stars formed earlier in galactic history from gas that had experienced less enrichment, fewer cycles of stellar birth and death. Then there's population 3. These would be the very first stars to ever form, created from the pure hydrogen and helium that existed right after the Big Bang. Zero metals. Nothing heavier than helium. Just the primordial elements produced in the first few minutes after the universe began. Nobody has ever confirmed a population 3 star. They should have existed. The physics demands it. The early universe contained only hydrogen and helium. The first stars had to form from this pristine material. But finding them is incredibly difficult because they all died billions of years ago. Population 3 stars would have been massive, much heavier than typical stars. Computer simulations suggest they weighed hundreds of times more than our Sun, possibly even thousands of solar masses. These monster stars would have burned incredibly hot and bright, pumping out tremendous amounts of energy. But they would have lived fast and died young, exhausting their nuclear fuel in just a few million years before exploding catastrophically. Those explosions were critically important for cosmic evolution. When population 3 stars exploded, they scattered the first heavy elements into space. Carbon created through nuclear fusion in their cores. Oxygen, nitrogen, silicon, all the elements beyond helium. These elements mixed with the surrounding hydrogen and helium gas, enriching it, changing its chemical composition. The next generation of stars formed from this enriched gas. They incorporated the heavy elements created by population 3 stars, becoming population 2 stars with small but measurable amounts of metals. Those stars lived, died, enriched the gas further. The cycle continued. Each generation of stars created more heavy elements, gradually building up the rich chemical inventory we see today. Every element in existence except hydrogen and helium came from this process of stellar nucleosynthesis. The gold in wedding rings, the uranium in nuclear reactors, the copper in electrical wiring, the aluminum in soda cans. All of it was forged inside stars, created through nuclear reactions in their cores or during their explosive deaths. Population 3 stars started this entire process. They were the first factories producing heavy elements. Without them, no rocky planets would exist. No life could form. The universe would contain only hydrogen and helium forever, with stars but no planets, no chemistry, no possibility of complexity emerging. Finding population 3 stars is one of the holy grails of astronomy. It would confirm our understanding of stellar evolution at the earliest times. It would show us what the very first stars looked like, how massive they were, how they influenced their surroundings. It would be like discovering a fossil from the first life on Earth, a glimpse into the absolute beginning of a fundamental cosmic process. The problem is that they're so old. Any population 3 stars still shining would be in the most distant galaxies we can observe, visible only as they existed in the very early universe. Their light would be incredibly faint, stretched by billions of years of cosmic expansion. Even James Webb struggles to detect individual stars at such tremendous distances. Instead of looking for individual stars, astronomers search for galaxies where population 3 stars might still dominate the total stellar population. These would be extremely young galaxies where the first generation of stars has formed but not yet died and been replaced by later generations. This is where a galaxy called JWST enters the picture. James Webb observed this object as part of a survey hunting for unusual galaxies in the early universe. When the spectrum came back, it showed something strange. Almost no oxygen lines. Almost no carbon lines. The spectrum was dominated by hydrogen and helium emission with barely any signature from heavier elements. This could mean the galaxy contains mostly population 3 stars. Stars that formed from primordial gas containing no metals, stars that haven't yet enriched their surroundings with heavy elements from their deaths. The galaxy might be so young that the first supernovas haven't occurred yet, or have just started happening, so heavy element production is still in its earliest stages. The interpretation isn't certain though. Other explanations are possible. Maybe the galaxy contains normal stars but the spectrum is showing us gas clouds rather than stellar atmospheres. Maybe the gas is unusually pristine despite not being truly primordial. Maybe there's some unusual geometry or dust distribution affecting what we observe. Confirming population 3 stars requires deeper observations. James Webb needs to look longer at this galaxy, gathering more photons, building up a stronger signal. The spectrum needs to show not just the absence of metals but the specific signatures that would uniquely identify population 3 stellar populations. Additional observations need to rule out alternative explanations. If the light is coming from gas clouds illuminated by normal stars hiding behind them, deeper observations might reveal those stars. If unusual dust is obscuring metal emission lines, infrared observations at different wavelengths might penetrate the dust. The search continues. James Webb is still relatively new, still conducting its initial surveys. As it observes more of the early universe, as it studies more galaxies from the cosmic dawn, the chances of finding confirmed population 3 stars increase. Each deep field image reveals new candidates. Each spectrum provides new clues. Some galaxies show lower metal content than others. Some appear younger, less chemically evolved. By studying many examples, by comparing their properties, astronomers can narrow down which objects are most likely to contain genuine population 3 stellar populations. The significance of finding these stars goes beyond just checking off an item on astronomy's wish list. Population 3 stars shaped the early universe. Their intense ultraviolet radiation helped end the cosmic dark ages by ionizing surrounding hydrogen gas, transforming the universe from neutral and opaque to ionized and transparent. Their supernova explosions enriched the first galaxies with metals, enabling the formation of later generations of stars and eventually planets. Understanding population 3 stars means understanding how the universe transitioned from its initial state of pure hydrogen and helium to the chemically rich cosmos we inhabit today. It means understanding how the building blocks of planets and life were first created. It means seeing the very beginning of the stellar life cycle that has continued for over 13 billion years, creating generation after generation of stars from increasingly enriched material. These first stars were the universe's original chemical factories. They took the simple raw materials provided by the Big Bang and transformed them into the periodic table of elements. Everything that came afterward, all the complexity and diversity of the modern universe, depended on that first crucial step. Finding them, studying them, understanding them would complete a major chapter in our cosmic history. It would show us the absolute beginning of chemical evolution, the point where the universe started becoming interesting, where the potential for complexity and eventually life first emerged from the simple aftermath of the Big Bang. Every discovery, every observation, every measurement is pointing toward one conclusion. Every discovery from James Webb isn't just answering questions. It's shattering everything we thought we knew. Something profound is happening in astronomy right now. We're witnessing a revolution in our understanding of the universe, a complete rewriting of cosmic history. Every week brings new observations from James Webb that challenge our models, contradict our predictions, force us to reconsider fundamental assumptions about how the universe works. The picture emerging from all these discoveries is clear. The early universe was nothing like what our theories predicted. It wasn't slow and patient, gradually building up complexity over billions of years. It wasn't methodical, carefully following the rules our computer simulations laid out. Instead, it was wild, chaotic, violent, impossibly fast. Galaxies appeared earlier than they should have. JWST 14 exists just 280 million years after the Big Bang, shining brightly when according to our models only small proto-galaxies should exist. It's not alone. Hundreds of early galaxies have been found, all brighter and more massive than predictions suggested possible. These galaxies formed stars at rates that seem physically impossible given the limited time available. JWST 140 creating hundreds or thousands of stars per year when the universe was barely 300 million years old. Gas collapsing, stars igniting, supernovas exploding, new generations of stars forming, all compressed into timescales our models said were far too short. Black holes grew to supermassive size when there wasn't enough time for them to grow that large. Canucks LRD Z86 containing a black hole weighing millions of solar masses just 570 million years after the Big Bang. LID 568 feeding at 40 times the theoretical maximum rate, gorging itself in defiance of physics. Little red dots scattered everywhere, hundreds of galaxies with black holes that dominate their total mass, breaking the fundamental relationship between galaxies and their central black holes. The cosmic web assembled itself faster than gravity should have been able to pull structures together. The Cosmos Web survey showing galaxy clusters and filaments already formed when the universe was just a few billion years old. 800,000 galaxies in a patch of sky smaller than your thumbnail held at arm's length, revealing a universe far more crowded with galaxies than anyone expected. Black holes don't sit quietly in galactic centers. They race through space at millions of miles per hour, kicked out by gravitational recoil or three-body interactions during violent mergers. They collide with each other, sending gravitational waves rippling across spacetime. They leave trails of newborn stars in their wake as they plow through intergalactic gas. We thought we understood how fast the universe is expanding. Two different measurement methods give two different answers, and James Webb confirmed both are correct. The Hubble tension is real, pointing to gaps in our understanding of dark energy, cosmic evolution, or the fundamental nature of spacetime itself. Every single one of these discoveries challenges our theoretical models. The simulations we spent decades developing, running on supercomputers, comparing to observations, refining carefully. Those simulations predicted slow galaxy formation. They predicted black holes growing gradually over billions of years. They predicted star formation happening methodically at moderate rates. They predicted structures assembling over enormous timescales. The real universe followed none of these predictions. It did everything faster, more efficiently, more violently than our best models suggested possible. The early cosmos was more productive, more energetic, more chaotic than anything our simulations captured. This isn't just surprising. It's revolutionary. It means our understanding of fundamental processes like star formation, black hole growth, galaxy assembly is incomplete. We're missing something crucial, some physics or some conditions that made the early universe behave differently than the modern universe. Maybe gas dynamics worked differently when the universe was denser and hotter. Maybe dark matter played a bigger role in the early universe than it does today. Maybe feedback mechanisms that regulate star formation in modern galaxies were weaker or absent back then, allowing runaway star formation to occur. Maybe the initial conditions coming out of the Big Bang were different than we assumed. Whatever the explanation, we need to fundamentally revise our models. The equations need adjustment. The assumptions need questioning. The parameters need recalibration. Every new observation from James Webb adds constraints, narrows the possibilities, points toward what the correct model should look like. This is how science advances. Not through smooth accumulation of knowledge that confirms existing theories, but through revolutionary observations that force complete reconceptualization. The Copernican revolution displaced Earth from the center of the solar system. Einstein's relativity replaced Newton's absolute space and time. Quantum mechanics revealed the probabilistic nature of reality at small scales. James Webb is triggering another revolution, showing us the early universe was fundamentally different than we imagined. The discoveries are piling up too fast to ignore, too consistent to dismiss as anomalies. The universe is telling us we got important things wrong about cosmic history. The most unsettling aspect is what we still don't know. We haven't found population 3 stars yet despite searching. We don't understand the Hubble tension or what it implies about dark energy. We can't fully explain how black holes grew so massive so quickly or why little red dots exist in such abundance. We don't know if the laws of physics operated differently in the early universe or if we're just missing some crucial environmental factors. These unknowns represent the frontier of astronomy. They're the questions that will drive research for the next decade or longer. Every one is an opportunity for discovery, for understanding, for expanding human knowledge about the cosmos we inhabit. James Webb is not just a telescope. It's a time machine showing us the universe's infancy. It's a reality check forcing us to confront how much we don't know. It's a revolution engine systematically dismantling old certainties and revealing new mysteries. The universe is bigger than we thought. More complex than we imagined. More violent in its youth than our models predicted. Filled with structures and objects that shouldn't exist yet but do. Operating under rules we don't fully understand yet. This is both humbling and exhilarating. Humbling because it reveals the limits of our current understanding, showing us how confidently wrong we can be despite decades of careful work. Exhilarating because it means there's so much more to discover, so many mysteries waiting to be solved, so much fascinating complexity hidden in cosmic history. The story of the universe is being rewritten in real time. Every observation from James Webb adds another chapter, another plot twist, another revelation that forces us to reconsider what came before. We're living through one of the most exciting periods in the history of astronomy, watching our cosmic origins come into focus with unprecedented clarity. The universe was wild in its youth. Fast, violent, productive beyond imagination. It created galaxies and black holes and stars at rates that still confuse us. It assembled structure quickly, efficiently, through processes we're only beginning to understand. We're not just looking backward in time when we study the early universe. We're looking at our origins, at the epoch when the first seeds of everything we see today were planted. Every galaxy James Webb observes from the cosmic dawn tells part of the story of how we got here, how the simple aftermath of the Big Bang evolved into the complex, structured, galaxy-filled universe we call home. This is just the beginning. James Webb is still operational, still observing, still gathering data every single day. More discoveries are coming. More surprises await. The universe has more secrets to reveal, more mysteries to unfold, more revolutions to trigger in our understanding. Every time we think we've figured it out, every time we think our models are complete, the universe shows us something new. Something impossible. Something that shouldn't exist but does. Welcome to the new universe. Bigger, stranger, more wonderful than we ever imagined. Thank you for joining this journey through the discoveries reshaping our understanding of cosmic history. We've witnessed galaxies that formed too early, black holes that grew too fast, stars being born at impossible rates, and mysteries that challenged the very foundations of cosmology. If this video opened your eyes to the universe's hidden wonders, hit that subscribe button right now. More incredible discoveries are being made every single week, and you don't want to miss them. Drop a comment below telling me, which discovery shocked you the most? Was it the runaway black hole leaving a trail of stars? The little red dots breaking every rule? The galaxy forming thousands of stars per year when it should barely exist? I want to know what blew your mind. Coming up next, we'll explore the Nancy Grace Roman Space Telescope, launching in 2027. It's designed to scan massive portions of sky simultaneously, promising to find galaxies even farther back than James Webb can see, pushing closer to the Big Bang itself. The universe is waiting. The mysteries are endless. Are you ready to keep exploring?